Okay, so in this lecture, we're going to briefly review some facts about bilinear forms on fields, and yeah, so this is going to be, in this section, we'll review basic properties of bilinear forms on a vector space. So basically the reason why this is important for number theory, so it turns out that this trace so the notion of trace from the last couple lectures, this actually gives rise to a really important bilinear form. So that gives rise to a bilinear form with the same name. And studying this bilinear form, it turns out, is going to be useful in showing that of the same name and studying this bilinear form is more or less how we prove that rings of integers are finitely generated Z-modules. Studying bilinear form. Leads to the fact that rings of integers are finitely generated Z-modules. Okay, so this is why we're going to be talking about bilinear forms. Okay, so first I should tell you what a bilinear form is. I guess let me give you the overview of what the lecture is going to look like. Okay, so first I'm just going to tell you what the definition is. Okay, then we're going to talk about gram matrices and discriminants. So these are ways of essentially, well, the gram matrix is a way of describing the bilinear form in a matrix. And the discriminant is a way to tell if your bilinear form is what's called non-degenerate. And then, yeah, I guess the third thing is kind of like non-degenerate bilinear forms. And the dual basis. Okay, so let's go ahead and get started with definition. So what is a bilinear form? So this is 19.1 definition. Okay, so let K be field. And let's say V is a let's just say K vector space. Okay, and what is a bilinear form? bilinear form so a bilinear form on V is a map. I guess is a bilinear map. So what do I mean by this? Bilinear map psi from V cross V. I guess maybe it's poor form to use the word you're trying to define in the definition, so I'll avoid that. So it's going to be a map from V cross V to the field K, such that basically it's linear in each factor. So for all C in K, I guess maybe I should say, let's say for all C1, C2, and K, and let's say V1, V2, U1, U2. In V, we have, so it's linear in the first factor, so psi of, let's say, C1, V1 plus U1, and then I'll just put V2 there. It doesn't really matter what I put in the second slot. It's going to be linear in the first factor, so it'll be C1 psi of V1 V2 plus psi of U1 V2. Okay, so this is linearity in the first factor. Okay, and then it needs to also be linear in the second factor. Okay, so this is going to be V1, let's say C2, V2 plus U2. It's going to be psi, it'll be C2 psi of V1, V2 plus psi of V1, U2. Okay, and this is linearity in the second factor. Okay, so it's essentially a way of pairing vectors. So the kind of like first example you would see in math is the dot product is a bilinear form. Okay, so the prototypical example is the dot product. Okay. This is a map. Yeah, I guess, okay, I'm not going to redefine what the dot product is. Hopefully by now you know what the dot product is. You can define it on Rn, you can define it on really any vector space. Any finite dimensional vector space at least. Yeah, so the prototypical example is the dot product. Everything else is kind of generalizations of this. Not every property of the dot product. Every bilinear form does not have every property that the dot product has. So, to continue this definition, a bilinear form is called symmetric. Okay. If, so for all U and V, it doesn't matter which order I compute their pairing. Okay. So I can swap the entries in psi. And this doesn't happen for every bilinear form, but when it does, they're called symmetric. Okay, and the dot product is a symmetric bilinear form. Okay. So these are the this is what a bilinear form is. The dot product is the prototypical example. There are other bilinear forms. Okay, so I want to move on to the second thing, which is Gram matrices and discriminants. Okay, so definition. So what is the Gram matrix of a bilinear form? So say let psi be a bilinear form on a vector space V. Let's say V is finite dimensional, okay? And a vector space V, finite dimensional over K. And further, let's say that we have a basis. Actually, okay, we don't, let's not presuppose these. So first of all, let's define what the Gram matrix is. So if, say, E1 through En is a basis for V, then the Gram matrix of psi with respect to this basis is, okay, so what is, how do I define the Gram matrix? I think I picked the wrong pen here. Is the matrix which looks like, so essentially you just take all the possible pairs of basis vectors and you form and you compute what psi those guys are, and that gives you an n by n matrix. So this Gram matrix, it turns out, tells you a lot about your bilinear form. Okay, the determinant of this matrix is called the discriminant. Okay, and this should have numbered this 19.2. Okay, so it turns out, so the Gram matrix is kind of all you really need to know about a bilinear form. So here's the 19.3 important remark. Bilinear form is determined by its Gram matrix in the following sense. There should be no apostrophe there. Its Gram matrix in any basis. Okay, so what do I mean by this? If, let's say, U and V are vectors in V, and let's say I know what they look like in the basis. So U is AI, EI, and V is BI, EI. Okay. Well then, if let's say A is the Gram matrix of psi with respect to our basis of EIs, then I can compute the value of psi by doing some matrix multiplication. Okay. Then psi of UV. If you use bilinearity in both factors, you'll find that this is the sum of the AI Bj psi of EI Ej. Okay, and this is the sum over I and j less than or equal to n. Okay, and it turns out that if you compute a little matrix multiplication, this is going to be the same as the vector of A's. So view it as a row vector, so take the transpose if you like, times the Gram matrix times the vector of B's. Okay, so essentially knowing the Gram matrix makes it possible to compute this guy's size. So like, it's not possible that two different bilinear forms have the same Gram matrix. So that's what I mean when I say determined by its Gram matrix. Okay. And so what do we care about this discriminant concept? So it turns out there's something called non-degeneracy. So definition, I guess there's a couple ways you can do this. I'm just going to define it as follows. Definition. A form, let's say psi, is non-degenerate okay. It's non-degenerate if, so this is the definition part. Let's say if the discriminant is non-zero. Is non-zero with respect to some basis. Okay. It turns out that I guess there are a couple like different things you could ask here. So like, you know, one concern is, so warning or like concern. The discriminant can be different for different bases. Discrim can be different for different bases. Okay. So this can certainly happen. However, it turns out that essentially changing the basis amounts to multiplying this guy by two invertible matrices. So if this has non-zero determinant, then with respect to one basis, well, multiplying by invertible matrices isn't going to change that. And we'll talk more about this in more lectures about the discriminant, like what happens when I change basis. But for now, you should know that this is a well-defined condition. The above is well-defined. Okay. So the next thing I want to talk about is like, okay, what is this non-degeneracy condition really saying? What am I saying when I say that the Gram matrix is invertible? Okay. So proposition the following are equivalent. One, psi is non-degenerate. So again, psi is a bilinear form on, let's say, a finite dimensional vector space. Okay. For psi, bilinear form. On a finite dimensional vector space. P. Okay, so as non-degenerate. 2, there's something called the left kernel. So the left kernel so what is the left kernel defined as? The left kernel of psi is the set of phi and v such that psi of v times x equals 0 for all x and v. Okay, so one way to think about this kernel, this left kernel, is saying that basically this bilinear form can't tell the difference between v and the 0 vector. So the condition I'm putting on, so psi is non-degenerate is equivalent to the left kernel of psi, which is this set, being trivial, i.e. just the 0 vector. So if my form is non-degenerate, then this left kernel, then basically by sticking vectors in the left, this form can always tell the difference between it and 0 by testing it on some vector in the right. Okay, and then the other condition is the symmetric condition, the right kernel. So you can imagine what the right kernel is. Sorry, oh yeah, no. Yeah, the right kernel is trivial. Okay. So non-degeneracy is really a condition about like how one way to think about it is non-degeneracy is a condition on how often the pairing of two vectors is 0. Okay, and I'm not going to fully prove this, but I'll give you a hint, basically. The fact that these are equivalent follows from remark 19.3. And the fact that a matrix is invertible if and only if it has like trivial, well, I guess if you're using like the first things you learn in linear algebra, trivial null space, trivial kernel. Okay. Yeah, essentially, this condition of being in the left kernel well, the condition of being in the right kernel basically says that you're in the kernel of A, and the condition of being in the left kernel is something like you're in the kernel of A transpose, something like this. Okay. And the final thing is somehow it's super important for the proof we're going to do, and it's a little confusing concept. So the final thing is basically a remark about dual bases. Okay. If psi is non-degenerate, psi is non-degenerate bilinear form, then essentially psi can be used to understand the dual space of V. Let's say a finite dimensional vector space V. And we've got this map. V maps to the map which sends X. So this is kind of a confusing thing where you have this iteration. Okay. This is a map from V to its dual space. So this map here, X maps to psi of V comma X, is a linear map on V. Gives an isomorphism. From V to V dual. Okay, so psi is non-degenerate. Okay, so this is where this non-degeneracy condition comes in. Then there's an isomorphism from V to V dual described by psi. Okay. If you've seen something like, well, if you've taken like an advanced linear algebra class, you've probably seen something like this before. And if you've taken any functional analysis, this is somehow an analog, or you should think of the Riesz representation theorem from functional analysis as some big generalization of this fact. But okay, that's beside the point. How do I know this gives an isomorphism? Well, I know they have the same dimension, so it suffices to check this is injective. Have the same dimension. So it suffices to check its injectivity. Okay, and I realize that the dual space may not be something that everyone watching these lectures is super comfortable with. Remember, this is the space of this is the space of linear functions on V from V to K. Lambda linear functional. So I guess really I can drop the word functional. It just needs to be linear. Okay. And a common, a standard fact from an advanced linear algebra course is that these two things have the same dimension. So I just need to check this map is injective. However, this is exactly the condition that the left kernel is trivial. This is exactly condition that the left kernel is trivial. Okay, so basically, if V isn't the left kernel is exactly the kernel of this map. V maps to this linear functional. Okay. So I guess you could tack on like a fourth thing, which is that this map here, V maps to X maps to psi of V comma X, is an isomorphism of vector spaces. Yeah, I guess you should also check, like, that this is actually a linear map and so on. Okay. So what's the importance of this fact? So why is this useful? Well, essentially, it's useful for the following. Okay, this tells me that, okay, if I have a basis okay, I'm gonna call this isomorphism, let's say, big psi. Okay. Say if I have a basis EI, okay, then standard fact from linear algebra, then I can construct a dual basis. So this is how you actually prove this fact I referenced earlier, that these spaces have the same dimension. A basis Fi with Fi of Ej. This is, it's 0 if I and j don't match, and it's 1 otherwise. Okay, so it's essentially the indicator function on whether the basis vector I plugged in is matches, whether the index of the basis vector I plug in matches the index of my linear functional. Okay, so this is somehow, I mean, this is essentially one way to think about this is these f sub i's just pick out like the ith coordinate. If you're thinking of v as like k to the n, this just picks out the ith coordinate of your vector. Okay, and that's a linear functional, and this is the dual basis for the ei or ej. And I can use this isomorphism psi to essentially translate that back into a basis for big V. So I'd let E sub I prime, this is going to be big psi inverse of E sub, big psi inverse of F sub I. And then what useful properties does this have? So I guess the collection of E sub I prime has the following useful properties, I guess. First of all, it's a basis. So this is a basis since Fi is a basis and psi is a big isomorphism. Big psi is an isomorphism, sorry. Okay, and the second condition is I can actually tell you what the inner product is. So, or I guess, sorry, not inner product. What my bilinear pairing is on the EIs and the EI primes. So, and furthermore, well, psi, little psi of EI, or, sorry, I would want to do EI prime EJ. Okay. Well, this is exactly this big isomorphism psi of EI prime. So this is now, I'm thinking of this thing as a linear functional. and v check of E sub j. Okay, so this is just by the definition of what this map big psi does. And, well, since EI prime is psi inverse of Fi, well then psi of EI prime has to be the Fi, so this is Fi of Ej, okay, which is, again, 0 if I is not equal to j, and 1 otherwise. Okay, so what conclusion can we draw from this? So this is going to end up being actually really useful in our proof. So, conclusion. For a non-degenerate bilinear form psi, and basis EI, I can find what's called a dual basis. I can find a dual basis for V. EI prime, where psi of EI prime EJ is 0 if I is not equal to j, and 1 else. Okay, and we're going to, basically, the plan going forward is psi is going to be the trace bilinear form. We're going to show this trace bilinear form is non-degenerate by computing the discriminant using a little Galois theory and our formulas for trace. And then, once we know the trace is non-degenerate, we can take a basis and get a dual basis, and it turns out this pair of bases is what's going to show that our ring of integers are finally generated in C modules. Okay. That's the plan going forward. So the next few lectures are going to be on computing discriminants and how do I tell if a bilinear form is non-degenerate, more or less.